Hi, my name's Raj Joshi. I'm a physics teacher from South London. Today we're going to have a look at nuclear energy, in particular different types of decays. This is aimed at an A-level lesson and it features on a lot of different exam boards. What I'll do is talk you through some of the content, and then there'll also be opportunities to pause the video for you to work some bits and pieces out. First, let's start with a recap from GCSE. You'll be aware of the three types of radiation that you've studied at GCSE: alpha, beta, and gamma radiation. You should hopefully remember those Greek symbols that appear at the start of the Greek alphabet to symbolize alpha, beta, and gamma. And you might be able to recall what they're made of as well. Alpha being that big helium nucleus that is the charge of 2 protons. It's quite heavy compared to the other two, and is fairly easy to stop, but is quite ionizing. Beta, on the other hand, you might remember as being an electron, having a charge therefore of an electron and the mass of an electron, being a bit lighter than alpha, a little bit more difficult to stop, but not being as ionizing. Gamma you might remember from your GCSE studies about the waves section, in particular the electromagnetic spectrum, as the highest frequency part of the EM spectrum. So gamma is really difficult to stop, but it doesn't necessarily do as much damage as alpha or beta. Because we're taking an A-level approach to this, I've put the charge in coulombs and the mass in kilograms. Make sure you take account of this when you fill out the table. Pause the video and have a go at filling it out. So here are the answers. When you did this in class, you might have not been completely satisfied with some of the demonstrations that your teacher would have showed you. Certainly with alpha, a single sheet of paper probably didn't do that much difference to the count on the Geiger-Müller tube, and certainly would need quite a bit of paper to cause complete shielding. Again with beta, a single thick sheet of aluminium foil probably didn't make much of a difference in terms of the thickness. Gamma as well needed quite a lot of lead to stop it. Actually, now that we're in A-level, we can maybe understand that the thickness of the paper or aluminium or lead determines the amount of radiation that's been stopped. You might have also been shown some applications. So the most common ones that teachers tend to talk about with alpha is smoke alarms. When the smoke gets between the alpha source and a detector, this will be registered and the smoke alarm will go off. With beta, we often talk about using it to measure the thickness of different things, for example in a paper mill. Whereas gamma is often talked about in terms of killing cancerous cells during radiotherapy. At GCSE, you'll be shown different sources, an alpha source, a beta source, a gamma source. But you might be thinking, how do we know which isotope will give off which type of radiation? At A-level, we start to get some clues about how to work out which type of radiation will be produced. In order to figure that out, we can look at what happens to the nucleus and how it changes after the radiation has been emitted. In the case of alpha, we'll see that the nucleus loses 2 protons and 2 neutrons. So the atomic mass will change by 4 and the atomic number will change by 2. For beta plus, what we'll see is that a proton will change to a neutron. So the total number of nucleons will stay the same. The atomic mass number will stay the same. But the number of protons will decrease by 1. For beta minus, it's the opposite. The number of protons will increase by 1. And finally, for gamma, the atomic mass and the atomic number will stay the same. We use this little M symbol to show that the atom before isn't quite stable. It's metastable. Once the atom emits the gamma radiation, then it becomes its stable form. Now that we've been through how different atoms decay when they undergo different decays, you can have a go at this task. Work out which isotope we get at every step along this journey. Pause the video and have a go. Hopefully you ended up with carbon-12. Now that we've seen how atoms are affected by different decays, we can try and visualize these decays on a graph. If we plot neutrons on the y-axis and protons on the x-axis, we can look at alpha, beta plus, beta minus, and gamma decays and think about how these will affect the number of neutrons and protons of any isotope that we plot on this graph. For an alpha decay, the number of neutrons will decrease by 2 and the number of protons will decrease by 2. So we can think of a vector like this, where the number of neutrons goes down and the number of protons goes down. This vector can represent an alpha decay on a graph against neutron number to proton number. For a beta plus decay, we'd expect the number of protons to go down by 1 and the number of neutrons to go up by 1. So we'd get a vector looking like this. And the opposite way for a beta minus. For gamma, the number of neutrons and protons won't change, so it'll stay at the same place on a graph of neutrons against protons. This way of showing these decays as vectors can be a little bit difficult to get your head around. You might want to pause the video and have a little bit of a think about that. And then, when you feel a bit more confident, have a go at drawing these vectors in AZ space, where we have the atomic mass on the y-axis instead of the number of neutrons. If we try and draw the NZ space for the entire periodic table, as well as all the unstable isotopes we know about as well, we can get a graph like we have on the right. The black dots are the stable nuclide, where the coloured dots are unstable isotopes that decay in different ways. So the black dots are a bit like plotting what we see on the periodic table in terms of the number of neutrons and protons. So when you've had a look at the periodic table, you may have noticed that at the start they're usually roughly the same number of protons as neutrons. But as we move further down the periodic table, there are much more neutrons than there are protons. We can see this on the graph as well. At the start, we have roughly the same number of protons and neutrons, so it follows that one-to-one black line. But as we get higher and higher up the graph, the stable nuclei become more neutron rich. This sort of makes sense. For very, very large atoms, we'd expect there to be lots and lots of neutrons, which are giving that strong force to keep the atom together, but fewer protons, for which the Coulomb force is making the atom want to fall apart. The different isotopes that aren't stable lie on either side of this black line. The ones that are above the black line are going to try to get to the black line by beta minus decay. Imagine that vector that we drew for beta minus decay. All of those atoms could use beta minus decay to get closer to the black line. The orange region is beta plus decay. So those would use beta plus decay to get closer to the black line. Whereas the yellow region need that great big alpha decay vector in order to end up as more stable nuclei. I hope that you've learnt a little bit more about nuclear decay. On behalf of the Science Learning Partnership, thank you and good luck.